What's up, everyone? Welcome to Simulation. We have a very special episode today. We are going to be talking about aerospace engineering, and to do so, we have Creon Levit joining us. What's up?
Thanks, Alan. Nice to be here. What's up?
Thanks for coming on to our show. Greatly appreciate it. And you have the perfect background to be teaching us about aerospace engineering with 32 years at NASA Ames Research Laboratory. Research facility, research center. And most people don't even know that Ames is in the Bay. People are like coming in like fresh to code at all these tech companies, and then we're like, by the way, there's a NASA center down by Google and Singularity University. They're like, what's Singularity University? What's NASA Ames?
Right.
Yeah. And so you were there for 32 years doing all this great work. Now you're the director of research at Planet.
That's correct.
And you guys are launching and operating the constellations of satellites that are imaging the Earth and giving us all this unique data.
The world's largest constellation of satellites, actually. We've launched over 300 satellites.
You're at 300 now.
Well, we don't have 300 in orbit at the present, but we've launched about that many.
Yes, and so meaning maybe 100 of them or so have already went offline or so?
Yeah, about 100 have re-entered. And launching is different than successfully making it to orbit. So that's the thing we can talk about a little bit.
We'll unpack that.
Yeah.
Okay, cool. All right, so let's start with you and your background. So, I mean, 32 years of work at NASA Ames. There's so much to uncover there. So, so walk us through.
Well, we're not going to be able to cover it all because one has a number of different careers in the space of several decades like that. But I came out of school with degrees in computer science and applied math and came to NASA Ames actually as a programmer back in the 80s. And brought some of the first Unix machines, which is what Linux kind of used to be called, to NASA, and some of the first internetworking in terms of workstations and supercomputers talking directly to each other.
We have a graphic. Maybe we should pull that up.
Oh, yeah, we have a picture of, well, this is a little before my time, but this is a picture of the internet in 1973 when it was called the ARPANET, and there were only a few dozen nodes on it. And if you look along the left-hand edge there, a lot of them say Ames. That's NASA Ames. And Ames was central to the Pacific backbone of the original internet, and it had the first trans-Pacific link on the internet, which is that line to Hawaii. And it had the first supercomputer on the internet, which is the Iliac 4 right there. And so that was really Silicon Valley that kind of condensed around that mid-California, West Coast backbone right there. Stanford, NASA Ames, and then, HP and Apple and all these companies came about, right? Xerox PARC. Anyway, so that was before my time. I was just maybe learning the very first
bless all of the humans in 1973
who put this stuff together. Yeah, it's just incredible. And I was just learning to code back then in like junior high or something. But came to Ames, worked on computers and networks, and then got seduced by physics, which was really my love, and there were so many physicists working there and all kinds of things. Particularly at the start for me was they were working on aerodynamics, and particularly computational aerodynamics or computational fluid dynamics. So I did a lot of work on that. I worked with Brewster Kaele's connection machine. Brewster Kaele and Danny Hillis had this supercomputer that they designed, and NASA bought one of them. I got to be friends with them and did computational fluid dynamics on the connection machine and flow visualization on the connection machine. That led me into this whole, 8 or 10 years of a career doing data visualization. And
that's such a crucial part of engineering, of being able to see the data in ways that are relatable and interesting.
Right, and especially when you've got these giant computers cranking on these, massive simulations producing like terabytes of data. I mean, the only thing you can do is to try and make pictures of it. And nowadays, everybody's heard about infographics and visualization, but what I was working on was of a different sort. Like we were trying to understand three-dimensional flows and understand turbulence and understand chemical reactions and stuff like that. So it's more of it's called scientific data visualization as opposed to like InfoViz, where you're trying to make something for a Facebook meme, I don't know what the protocol is for moving forward on the images.
Let's go to the next image. We'll just ask Ronnie.
Ask Ronnie, we'll go to
okay,
so I eventually ended up doing some software years later for multidimensional data visualization of really large data sets in real time. And this happens to be a remote sensing data set, which kind of presaged my work at Planet. But the idea is there's all these different spectral bands of information, and you can draw boxes in different colors in different projections of the high dimensional space and see them in other projections, including an XY projection on the surface of the Earth. So this is just a general technique that we did a lot of work at Ames classic technique called linked scatter plots, where you have a whole bunch of different projections of multidimensional data into two-dimensional projected planes, and then you highlight some points in one of those projections, and they get highlighted in all the projections. So you draw a yellow box down here, and the yellow points light up everywhere in all the different views. So yeah, that was a fun project, and I still use this program all the time.
I want to ask this. So what is the key importance of taking three-dimensional data and putting it on a two-dimensional surface?
Well, I mean, you have to put it on a two-dimensional surface to see it on a display. Yep. Almost all the time when we talk about 3D graphics, we're really talking about 3D projected down to 2D graphics, with some exceptions. We can
click and drag and move it, right?
But what this is like 10-dimensional data that's being projected in a whole bunch of different ways. Imagine three-dimensional data, there's all sorts of ways to project it down to 2 dimensions, all different views you can have.
Right, yeah.
With 10-dimensional or higher dimensional data, you can have even more views. But again, to put them on a screen, they have to be 2-dimensional. So all the views hide something.
Yes.
And so you have to be looking at it from multiple views at once. And this was called viewpoints, because it was sort of a pun. All it did was draw points, and it viewed points from multiple viewpoints. So anyway, this continues to get reincarnated in new operating systems and platforms. And we did, I also got really into chemical reactions and nanotechnology, co-founded the first federally funded Nanotechnology Research Center, which was the Computational Molecular Nanotechnology Group at NASA Ames. This was in like the 90s. Early to mid-90s.
Computational molecular nanotechnology.
Yeah. So basically it's simulations of atoms and molecules for nanotechnology purposes.
Cool.
We didn't do that much real chemistry in the beginning. And this is my colleague Chris Henze many years ago. We had this cool thing. I mean, this is sort of a fake rendering here, but we had the stereo display and this big table where people could all wear the glasses and see the 3D images. And then you could reach in with this wand and grab atoms and pull them, and it would pull back on your hand.
That's
and
cool.
Then eventually the bond would snap and it would come out.
Yeah.
So we had this system for sort of doing what we called virtual mechanosynthesis, sort of prototyping and modeling what a Drexler type of nanoassembler might do. And that was a lot of fun. We did a lot of different virtual reality projects there. They didn't really get a whole lot of traction because back then virtual reality was too slow and clunky and expensive. So, but it was fun, and what eventually turned out to get traction were these things that just ran on a workstation or a laptop, you know, so everybody could have it. But a lot of the techniques crossed over.
And this is becoming more and more of an applicable way for people to learn, is to immerse themselves into a three-dimensional world where they can physically grab things and move them around.
Well, that's always been the draw. It's always been the hope. I was part of what I like to call the first VR bubble, and so we'll see how this second one works out.
Hopefully not towards only entertainment and distractive purposes, but let's do more towards educational purposes, enriching purposes.
Yeah. It'll be interesting to see how that plays out. You know, I'm not a VR AR expert anymore, but I'm interested to see what happens. I think VR is probably a little narrower than some people hope it to be, but AR may, I think, very well become ubiquitous.
Yes, correct.
Yeah. So, and I did, this got me really into chemistry, and I did a lot of quantum chemistry simulations for a while. This thing here on the screen is at the time, a very state-of-the-art simulation and graphic of the quantum mechanics of water molecules forming H2 and O, and then bonding into H2O.
Whoa, and that's what this is?
Yeah, so
that does look, that looks
like
H2,
and this is O, and this is the quantum mechanical technically it's the Laplacian of the charge density, but it's a particular aspect of the quantum mechanical wave function
That's
that has
so interesting.
a lot to do with reactivity and chemistry. And
I've never actually seen this before. That's so interesting.
Well,
so there's water.
There's water,
Yeah.
visualized in a particular way according to the quantum mechanical wave function, and then it's separating into H2 and O and reforming. So that was just
these naturally form. H2 and O naturally tend to.
Oh yeah.
Yeah. In such copious amounts that it makes oceans.
Yeah.
Yeah.
Right. Well, this is coincidentally enough. This is kind of the reaction that takes place in a lot of rocket engines. You know, if you have a liquid hydrogen, liquid oxygen rocket engine, then you're taking hydrogen, H2, and oxygen, and forming water, which is what the exhaust gas is.
It's what the exhaust gas is.
Yeah.
So, but is it?
And a huge amount of energy gets released when the oxidation happens.
Okay. So
it doesn't form water; it forms extremely high temperature, high velocity water vapor.
Is that what, when you have liquid hydrogen, liquid oxygen in a rocket?
In a combustion chamber inside a rocket.
They're combusting.
Yeah, they're basically exploding, but we call it combusting because it's inside of a rocket. But a rocket is pretty much like a contained explosion inside the combustion chamber, and then the exhaust gases go rushing out the back. Yeah,
but they're not combusting here. Just quick, explain to us, like
well, this is at the molecular level, and this is just very idealized. Like it's in vacuum, one molecule, you know, and they're just it's just an animation of the formation and then the disruption. It's really kind of a technical quantum mechanical investigation here, but it led us to work on much bigger molecules and much more elaborate visualizations. And so I always have a love for this quantum chemistry. And quite frankly, this is a good example. Here's the thing. People think, oh, quantum mechanics is so mysterious and chemistry is such a mysterious confusion. I think that actually three-dimensional visualization, perhaps virtual reality, would indeed really help people understand chemistry and molecules.
Definitely.
That is that's why I was
doing
doing
this. Yeah.
I mean, this is not like, it's not like anybody really needed to know about how water is created, but they had never really visualized molecular quantum fields in this level of fidelity and detail.
Correct.
So that got me some followers, if you will, although this was in the late 90s, so the followers meant something different. But yeah, went to a lot of conferences, showed more and more movies of these reactions, worked on our team at NASA on rocket fuels and biology and drug interactions and some weird kind of things that were off the path for NASA. And then, well, let's see, skipping forward a bit, then we had eventually this new director come to NASA Ames, Pete Worden. You should have him on your show.
We'd love to have Pete
Former
Worden.
Air Force general and sort of an astrophysics professor. And he collected smart people throughout his career, made friends with them, set up a network. And then when he was appointed to be the director of NASA Ames, he kind of reached out to all of these smart people and he said, you know, now's our chance to make a difference. Let's come and disrupt and revolutionize the way things are done at NASA. Let's do small satellites. Let's do, you know, advanced IT and cloud computing. Let's, you know, really try and take more risks with smaller projects instead of huge projects where you just spend decades trying to buy down the risk. And he got a lot of his brain trust to come quit their jobs and move to Silicon Valley and join him at NASA Ames. Now, I had already been there for like 20-something years, and I saw this new development happen, and then I was like, okay, I'm going to become friends with these people because they're obviously pretty cool.
Yeah.
What a breath of fresh air.
What a breath of fresh air to take on riskier, smaller projects to explore into new categories that are that have potential to really, one of them blows up, and that's a big deal. It's like putting a lot of eggs into different baskets.
Yes, exactly. It's kind of like, I guess, the venture capital portfolio approach, where you invest in a bunch of high-risk things and I hope that at least one of them pays off. Well, one of them that did pay off was Pete's emphasis and enthusiasm for small sats,
yes,
nanosatellites and small satellites, and you know, to kind of fast forward a little bit.
Because satellites prior to the whole idea of small sats were massive, right? They were the size of cars or school buses.
Exactly. Satellites tended to be very huge and cost hundreds of millions of dollars or more. And then small satellites started to happen, and that was in like the 90s. Well, it's complicated. The very first satellites in the 60s were small satellites because that's all that people could put into orbit. Yeah. But once the rockets got big, things got big fast, and people kind of forgot about the really early satellites that were, you know, the size of, you know, that you could hold in your hand.
Like a loaf of bread.
A loaf of bread, or some of them were strange sorts of shapes like icosahedrons and octahedrons, and people tried all sorts of things. Spheres, you know. And then, but fast forward to, you know, the mid-2005 area, this renaissance or like rebirth of nanosats happened. Small sats had, in the sense of like sats that only weighed a few hundred kilograms, they'd been happening in the 90s and stuff like this. But because of Moore's law and the, you know, huge increase in sophistication and power of microelectronics that were small and didn't weigh very much, in the 2000s you could start to build satellites with a lot of sophistication that were small, at least in theory. Nobody was really doing that. Various universities and stuff were building and launching these little CubeSats, but they were pretty crude. So a bunch of people who I worked with at NASA, who were, many of them were Pete Worden's proteges, and others joined in, were working on a nanosat project at NASA Ames called PhoneSat, and then a bunch of them decided, hey, we could really do something here. We could make a nanosat like the size of a loaf of bread that would actually, in large numbers, provide a very useful service, imaging the whole Earth at moderate resolution every day. And Will Marshall, the CEO of Planet, and Robbie Shingler, his co-founder, and a bunch of other people, most of whom are still at Planet, started the company in the garage at Rainbow Mansion, where we all live. Oh, we have a picture of the garage, I think, yeah, at some point. Anyway, and, oh yeah, there it is. There's the garage in Cupertino, you know, the same old story, and there's on the front, on the table, on the front edge of that table, is our first, one of the first satellites called the Dove. Satellites tended to always be named after birds of prey, and so the founders of Planet wanted to name it after a bird of peace instead.
It's a good whistle. That's a good one, Ron.
So yeah, so that...
Satellites were named after birds of prey?
Well, lots of aerospace things, airplanes, satellites, yeah.
Yeah, yeah.
A lot of times they were.
So it's nice to have a peaceful...
Yeah, well, the whole idea was to build these things to help the world.
Yes,
okay.
Correct.
Many people had built satellites to try and help the world. There had been lots of Earth imaging satellites built before these, like Landsat, and also maybe Rapid Eye, which we'll talk about. But these were the first Earth imaging nanosats. And these were different than the sort of university-style CubeSats that had been made. These had high-speed radios, like miraculous radios. And
as in the communication was very fast.
Yes, so because you need that down from space, at least you need very fast communications if you're going to be taking high resolution images.
Yes.
You have to get those images down to Earth. So these had, you know, high quality telescopes in them, high megapixel count digital image sensors in them, all the other little things you need in a satellite, like computers and memory and attitude control systems, so you can tell which direction you're pointed and then point yourself in a particular direction.
Yes, yes.
You know, star cameras, horizon cameras, sun sensors, reaction wheels, which allow the satellite to point in different directions, and as well as radios to receive commands coming up, and high-speed radios to send the images back down to Earth. And so one of the early Planet radio engineers, developed this really sort of brilliant high-speed radio design that was, you know, the size of a book of matches instead of the size of a shoebox, like the other radios that people were selling.
It's a big deal.
And in the very first one of those radios that we launched in one of these early Dove satellites, you know, it came over to the ground station and it sent information down to the ground station, and in that one 10-minute pass over that ground station, it downloaded more information than all of the NanoSats that had ever been launched had downloaded in their entirety. So,
wow.
That radio took us, that radio and the images, these things, the very first images that came from these satellites were actually good. You could see trees, you could see houses, you could see rivers and forestry, and, you know, you could really tell to some extent what was going on in color, and you know, it worked. And so the idea was to build a distributed constellation of about 100 of these. And so that took a long time well, not a long time in space years, but it took, you know, like 5 years went by, and now we have over 100 of these things in orbit, close to 200, and they are way higher quality than these early ones. They capture much wider field of view, they're sharper, they're taking in many spectral bands, and they're bringing down about, I think each one brings down about 1 terabyte a day.
Whoa. Okay.
I might be slightly wrong about that, but we're roughly within the order of magnitude.
Let's start unpacking some of the things that you've been teaching. So, as technology has become better over time, the technology inside the small sats has become better. So we've been upgrading the technology.
A lot of the technology has become better. Some of the technology was kind of already mature, like telescopes. People have been building telescopes for like 200 years, or 400 years if you go back to Galileo, right? But a lot of the telescope technology is fairly mature, and some of the satellite technology was also fairly mature. We just miniaturized it, and I mean literally just made it smaller.
Miniaturized the radio transmission. So let's unpack some more. So as the small sat is orbiting Earth, and we'll show some orbital mechanics stuff, that as it's orbiting, it can only, you said there's about a 10-minute window as it's going over a station, a ground station.
Right. Ground stations are those things that have dishes. They look like big satellite dishes because they are satellite dishes, and they can steer, so they can track the satellite as it's going overhead.
Yes.
Because all these satellites, our satellites, are in low Earth orbit. So they don't just sit there at one spot in the sky like most communication satellites do.
Low Earth orbit is about 200 miles?
Yeah, roughly speaking, 200-300 miles, yeah.
And then you're moving you're moving satellite on Earth. It's the ground station.
The ground station is a dish that tracks the motion.
The dish is tracking the motion and receiving the signal as it's going overhead.
Right, but it takes about 10 minutes for the satellite to go from horizon to horizon.
So you get a full 10 minutes of data collection, and you can, like you said, you can get a whole terabyte in a day as it's passing in different...
It's going to... Yeah, the geometry of the satellites and the ground stations and the rotation of the Earth is complicated.
Yes.
But if you have enough ground stations, then each satellite can usually talk at least once per orbit, and the orbit is about 90 minutes, so it can make several contacts per day.
Yes.
So you can get down a lot of data from a satellite, and the more ground stations you have, to some extent, the more data you can get down, and the better your radios are, the more data you can get down. And the lower your altitude, to some extent, the more data you can get down. There's all these different trade-offs. And this whole thing is orchestrated. You know, I mean, in the past, you'd have hundreds of people operating one satellite, and everything would be planned in great detail. We have the opposite situation. We have like one person operating 100 satellites. So everything is automated, and everything is run in the cloud, and the sequencing is kind of more like, it's kind of like air route management. Like you've got all these satellites going overhead and all these ground stations in different places and different priority of information on different satellites.
Yes.
So you have to have a fairly sophisticated scheduling system, kind of like an airline scheduling system where you've got gates and airports and flights, and you have to, you know, you have to try and optimize a lot of different things at once and be ready for problems, because inevitably something's going to fail or not work. You know, you won't make like satellite come over, you don't make contact with it. Now what do? You have to reschedule everything.
Make contact with it. Yeah, I was envisioning the small sat moving and communicating with one ground station, and then it gives a certain amount of its data, and then it's orbiting a different part of the Earth, and it communicates with a different ground station, gives the rest.
That's exactly what it does.
And then you guys at home are compiling that and making sure that it's giving all of its data. Then you have to clean the sat of its data and enable it to have more.
Oh, and it's more complicated than that even. It might start to fill up before you've gotten everything down, and then it's like, then what do you do? And then you're all of a sudden like maybe something's wrong with one of the solar panels and the batteries are getting low, and you have to prioritize charging the batteries. So when you're charging the batteries, you can't necessarily be taking pictures of the Earth or sending data down. There's all these different things that the satellite has to do to maintain its health, and so that stuff all has to be scheduled, and you have to have margins. Like you never want to actually brown out, right? So you want to be keeping track of your battery charge so that you don't get to a state where you're, you know, needing some emergency kind of protocols where it's basically useless. I mean, every one of these satellites up there, even though they're small and even though they're inexpensive, they're a sizable investment, right? So you want to keep them.
So a couple quick questions. How big is the team now?
I think the team at Planet is between 300 and 400 people. If you count
that's huge.
If you count Berlin, and you count San Francisco, and you count Mountain View. Yeah, some of that has come about through acquisition.
Yes.
We acquired a company called RapidEye. I think we have a picture
of the
RapidEye satellites,
which
are like a set of larger satellites. And that, no, it's something else.
But
we can talk about space debris too. I forgot all about the space debris stuff.
Maybe let's do a quick visit to space debris. Ron, go back one, and then we'll get to the team and more. So with orbital mechanics, I mean, this was kind of what we were describing before, is that the satellite is going overhead, and then this would be just like a facility of a ground station where you're connecting. I know this is the laser facility, but I'm just saying that this is how you would get the information, and then it would go continue collecting information, etc. But this is when you're actually trying to help make sure that the orbital mechanics of the satellite are staying in proper trajectory.
Well, it's not so much the satellite that this little sphere that it's
debris
is the idea is that it is a piece of space junk that has no propulsion and has no active capacity to do anything. It's just following Newton's laws, basically. And we're tracking all this stuff. Well, Planet isn't. We're tracking our stuff, but the governments of the world, particularly the US government, has what's called a Space Situational Awareness Network. And many dozens of different kinds of radars and telescopes all over the world that are trying to keep track of as much of the objects in orbit around the Earth as they can. So basically they track everything that's, say, 10 centimeters in size or larger, and some stuff that's smaller. Now we're getting better radars that can track stuff that's smaller. So they're tracking tens of thousands of objects that are in orbit.
And if we go to the next slide quick, you can see all of the crazy pieces of space junk.
Yeah, except this is a difference. This is a simulation, again on a big multi-panel display that we developed at NASA Ames called the Hyperwall, and this happens to be Will Marshall, although he's in the shadow there.
But that is an actual, isn't it not? Or is that the simulation? That looks like the actual.
That may be a visualization of the actual number of tracked objects. The bottom ones with the huge cloud are a simulated catalog of everything down to 1 centimeter in size that's orbiting the Earth.
That is absolutely. How did we do that already? It just seems like
how did we get that much junk up there?
We've just been launching for like 50, 60 years. How did we manage to get all that shit up there?
That's a long story. One is that, you know, earlier on, nobody cared about space debris. Nobody thought it would ever be a problem. because space was so big, if you will. And so early on, there weren't really any rules or guidelines. You'd launch stuff and they'd like have all these explosive bolts and different things to make this rocket stages separate and to deploy the satellite. Like they'd deploy the satellite off of the rocket and like pieces would go flying because who cares, you know? It was like a typical, you know, pollution kind of situation at the beginning when people don't think about long-term consequences.
Yes.
How do you, like colliding with space junk when we go to the space station and stuff like that? How do you avoid, you know, getting hit by
colliding with space junk?
Yeah.
Well, there's a lot of different systems. The first system is this tracking system. So you try and keep track of where it is, or at least where the really dangerous pieces are, which are the bigger pieces. And if you're keeping track of where they are, you just have to be very careful to not launch in any sort of a trajectory that's going to intersect one of them, and to, in the case of the space station, they do debris avoidance maneuvers. They'll get warnings like a few days in advance that there may be a close approach with a piece of debris, and since the debris can't move, the space station will actually, it has little and motors on it for, you know, little rocket thrusters on it, and it can go very slowly, move a little bit, but if it does this, it'll get out of the way. Now, if they're still afraid, like sometimes it moves out of the way, but the predictions weren't so good because the tracking wasn't so good, and maybe they actually moved even closer into the path of the oncoming object. So then they will actually, they have some shields on the windows and stuff like that that they'll close, and then they'll go like actually get into the capsules and get ready to abandon ship until the close approach has passed. And this has happened a number of times, and it's
I couldn't imagine losing the space station.
well, and that's the other problem, is that if something collides with the space station, or if anything collides with anything, it makes a big cloud of more debris.
More debris.
And, you know, that has actually happened a few times.
So things are colliding and making even more debris.
Yeah, so there's this whole possibility of a runaway chain reaction that could actually make space pretty much unusable by humans, at least for, you know, decades. Eventually, most of the stuff in low Earth orbit comes down because there's some atmospheric drag and there's solar radiation and different things that serve to eventually bring it down. But in higher orbits, like 1,000 kilometers or 2,000 kilometers, stuff can stay up for centuries. Now, of course, there's more space as you go farther away, but
this is horrible. But
this is this thing which is sometimes called the Kessler syndrome, this runaway chain reaction of space debris, which may or may not be happening. I mean, that's a whole
the fact that it's completely run away already versus if it's where it is now.
Yeah, it's probably at a place where, you know, obviously if we stopped if we stopped all collisions between large objects, it would get better because there's a natural cleaning that takes place from the atmosphere.
That's a very important thing to do, is to figure out how to do that.
So that's what, so people have come up with all kinds of schemes for getting rid of space debris. Oh, they want to send up satellites with nets to catch stuff, or harpoons, or giant balls of sticky glue, or magnets, you know, and all these things are very expensive, and it's unlikely that anyone is going to spend $50, $100 million, you know, to go catch one or two pieces of space junk.
Debris,
And B, every time you try to catch a piece of space junk, you actually, if you screw up, you can become a piece of space junk.
It's even worse. Yeah, so we just have to have a better long-term foresight into what is going on here and figure out how to clean things up a little bit to make it even easier for us to
we came up with
forward.
We came up with a plan which was slightly different. Our plan was that you monitor everything, which is already happening. I mean, not everything, but everything that's large enough to see by radar or telescope. And then when you see that there's going to be a collision, particularly a collision between two pieces of debris, which there's where you really can't tell one to get out of the way. I mean, nobody's got operating thrusters or anything like that. It might just be like a piece of a bolt or somebody's
Is that where the laser comes in?
That's where this laser idea comes in.
So go back one, Ron, quick. So that's where this laser idea comes in.
Yeah, the idea of the laser. So the idea is you track, you predict a collision or close approach. You can usually never really predict a collision. You predict a close encounter, if you will, between two pieces of debris. You track them, get their trajectories locked down, have some lasers on telescopes, point these lasers at the debris and just shine the light on the debris. And you might say, well, what's that going to do? But it turns out that the radiation pressure over the course of several hours of this, which you could do over the course of, say, 2 or 3 days, with maybe 1 to 10 of these laser ground stations, that radiation pressure, photon pressure, light pressure, or light force, which is what we called the project. We called it Project Light Force. That would be enough to nudge the debris out of the way so it doesn't encounter this collision.
Which possibly moves it into collision course with another.
Well, you try and keep track of all this stuff by tracking everybody, and you don't move stuff out of the frying pan and into the fire, ideally.
Yes, correct.
And it doesn't have to work all the time. It just has to work statistically enough of the time to slow the collision rate, to slow the growth rate to the point where we don't have a runaway situation. And
so let's maybe go back to Planet now.
Well, let me just say one thing about this. This is actually being done now. We had a partnership with the Australian organization that does laser ranging and stuff like that at Mount Stromlo Observatory in Australia. And they're actually setting up a system to test this out, not just laser tracking, but actually laser nudging. And you might think this requires some kind of giant weapons grade, death ray, but no. This requires a laser about the size of a laser that's used in a big laser cutter in an industrial manufacturing facility, and it requires a telescope that's like a 1 meter or 1.5 meter class telescope, and there are hundreds and hundreds of those all over the world. And so this whole system could set up and run autonomously for a few $100 million with enough of these laser stations.
We could get in full control of space debris and making sure.
Well, I wouldn't maybe go that far, but we could do a lot.
Light force could push it enough to get out of orbit potentially as well.
I don't think it could do that.
Okay.
No. And it's not a weapon. Like, it's not going to blast, vaporize anything. It's just nudging. It just nudges it with about the same pressure that the light from the sun nudges stuff, which it does do. And that's actually a significant force that you have to take into account when you're calculating satellite orbits, the solar radiation pressure. So anyway, this is being continued to be worked on. Sometimes I get frustrated, and I think that the reason the U.S. isn't doing it is because it's not expensive enough. Like, it's, like, they're like, what, a few $100 million? What's in it for me? So it's like, but the Australians, bless them, are continuing to work on this. And meanwhile, we do what we can at Planet with 200 satellites.
Let's show some of those. Okay. Yeah. Let's move on to maybe 2 slides forward, Ron.
Try to be good citizens and get ourselves out of the way when we are. Okay. All right. So here's this. I think 42 or 38 or something like that. Dove satellites.
Okay. This is the Dove satellite.
Right. They all have these little silver carrying handles attached to them, so that they can be stacked on top of each other and everything and not mess each other up. These were in I think the Netherlands or something like that, being integrated into a launch deployer system that then got shipped to Russia to be integrated onto a Soyuz rocket, and these satellites are now in orbit.
So, and as we look at them, we see that this here is our solar cells that are going to fold out, and we'll show those in a bit. And then we have the telescope sits on this rocket. It would sit on this side of the rocket.
On the satellite.
On the satellite. Sorry, on this side of the satellite. It would open up, and then the telescope would be able to capture the light.
There's kind of like a lens cap over the telescope when it's in this stowed configuration, and the lens cap pops open and becomes a radio antenna. And the solar arrays pop out like wings.
Yes.
And
we'll show that as well. And then this is where the camera and other optical measuring gear, radio is
there's electronics and radios and stuff crammed in all over the place. Every cubic centimeter is filled up because these things are very dense. They're much more dense. They're dense like a laptop computer, more than they are like a typical satellite.
And then what does that weigh?
I think about 4.5 kilos.
That's really light, actually. But yeah, okay, cool. Let's go on to the next one, Ron.
Here's
this is Rapid Eye.
This is the Rapid Eye constellation, which we also operate. That was launched about 10 years ago, about to have the 10th anniversary of Rapid Eye. They're still up in space going strong. And Planet acquired that constellation and the group of people in Berlin and Canada who were managing it and processing the data as part of a merger with Blackbridge Rapid Eye. And so these satellites are interesting. They're about the size of maybe a large mini fridge, like that one you have in the corner. And so they weigh maybe 120, 130 kilos. And for their time, they were considered small sats, and technically they still are small sats at like 150 kilos. And they were the first Earth imaging satellites produced on a production line. Like they made 5 of them in parallel, and they launched all 5 of them on one rocket. And they were sort of the pathfinders and pioneers in this idea of an Earth imaging constellation rather than like 1 or 2 special purpose, super expensive satellites.
That's great. This was launched in 2000?
2007 or 2008. 2008, I think.
Cool.
Built maybe over the year or two before that. But
cool.
Yeah, this company was kind of, the company that built them, Surrey Satellites and Space Technology, were kind of the inspirational mentor company for Planet.
For Planet, cool. So this is our first step into the small sat constellations
for Earth imaging.
For Earth imaging,
right?
Cool. This is Rapid Eye, and we were talking about Dove earlier. Ron, let's go on to the next one.
Oh, I don't know. Is there a next one?
Yeah, there is. We still have the full Dove image as well.
Oh, here's some.
Doves being deployed from the ISS.
There's Dove being deployed from the space station. Which we don't actually do anymore. The space station was a great kind of subsidized ride for us.
Because you go on the commercial resupply missions?
Exactly. But then they have extra space. They sell off that space pretty cheap. And also, quite frankly, the government...
That's our 15-minute timer. Thank you, Ron.
And quite frankly, the U.S. government and other governments are trying to encourage, let's just say politely, they're encouraging commercial use of the space station. So we were one of the big commercial users, and they encourage it by giving relatively cheap rides for gear up there. And our satellites went up there, and they would deploy them. And it's not really the orbit that we prefer, but it's an inexpensive ride. And we did a lot of testing from the space station because we could go up pretty frequently, and we'd try out new technology. And we got to go through a lot of iterations of our satellite design by deploying from the space station. But now we tend to just take rides that go to the orbits we want.
And yet this is maybe a key point to address. Now, why is this 250 miles up or so? Why is this not the ideal orbit? And what is the ideal orbit? And now how do you launch up?
Well, that's a bit of a technical matter. But here's the thing. If you're taking pictures of the Earth every day, you would like for the lighting conditions to be the same every day to the extent possible. Now, obviously, you have weather and certain things that make the lighting quite variable. But let's say on a clear day, you'd rather probably not have the light coming from all different angles depending on what day it is. In the space station orbit, that's what happens. When you go over, Chicago or whatever it might be, it's always at a different time of day. With the orbits that we choose to go into, and most Earth observing satellites choose to go into, they're called sun synchronous orbits, and it's a kind of a technical thing.
So you're going over Chicago at 2 p.m. every day.
Exactly, right.
Interesting,
exactly.
And that way you can image it.
That way when you see changes from one day to the next, they're not just changes in lighting angle.
Exactly.
They're changes in something that actually happened. It's not just shadows moving around, because that's not really all that interesting.
Okay,
I mean, you can use the shadows to learn things about three-dimensional structure, but But if you're trying to do things like monitor crops and monitor the movement of ships and this sorts of thing, then you like consistent lighting. And there's one set of orbits that have that.
Teach us about that as quick as we can, if possible.
Okay, here's the situation. the Earth is not a perfect sphere. The Earth is more like a football, right? Or a pancake-ish sort of thing. It's like that guy you've got on the table right there.
Yes.
Right, that egg-shaped thing. It's wider at the equator because it's spinning and it bulges out at the equator. Well, if you have a satellite in orbit around a non-spherical object, and the orbit is at an angle, the orbit will tend to precess. The orbital plane does not stay constant. Around a sphere, the orbital plane would stay constant with respect to the fixed stars.
If it's a perfect sphere.
It's a perfect sphere, but since the Earth is not. The orbit, what's called precesses. The orbital plane precesses.
Yeah.
Now, that would seem like it's even worse, like the orbit keeps changing, precessing, but you've got to understand, if it didn't precess, it would stay fixed with respect to the fixed stars, which would mean as the Earth goes around the sun, the time of day is always going to be changing when you're going over Chicago, as we were saying. But if the orbit is precessing and you can get the orbit to precess exactly once per year, now the orbit precesses with respect to the fixed stars once per year, but that's exactly what the Earth is doing going around the sun once per year, and so that's called a sun synchronous orbit. So it keeps the sun relatively in the same location all the time. And anyway,
so then once per day you're orbiting the same location, or is it multiple times per day you're able to, photograph the same location at the same time?
No, it's really that the angle between the sun, the Earth, and the satellite is relatively constant.
Correct.
That's what you want to keep constant.
But that enables you to photograph Chicago at 2 p.m. once per day, or multiple times per day, or...
Well, that's also complicated because that depends whether
you couldn't multiple times per day.
Well, you could multiple times per day if you're willing to not look straight down all the time. If you're willing to look to the side, you might pass Chicago more than once per day. You've got to look to the side to pass it once per day. It takes 100 of our satellites, roughly speaking, looking straight down to pass everywhere once per day.
Okay,
but that's if they're looking straight down.
I gotta ask though, would it take a lot of energy to keep the satellite in perfect orbit around just Chicago if you just want to photograph Chicago?
That you can't actually do that.
It's impossible to do that.
Well, impossible is a strong word.
Yeah.
It's completely impractical to do that. Now you can have a satellite in geostationary orbit, and there it's at the equator orbiting once per day. So the Earth, it's over the same spot of the Earth at all times, approximately, and that is what communications satellites do.
Yes.
Even that, because the Earth is not a perfect sphere, and the moon and things, it never works out exactly like it does.
Are these things referenced in the video that we have as well?
No, the video that we have is kind of a 1 or 2 minute summary video of the planet story.
Well, let's do that. Let's do this next image. Let's do that, and I will unpack all of this in more detail, hopefully at a future aerospace engineering episode, because there's so much ignorance that I have in that I'd like to understand more about.
It's a fairly complicated bit of business, orbital mechanics. I mean, people spend their lives studying orbital mechanics. We have quite a few specialists at Planet in orbital mechanics, and yeah, there's a lot going on there. But the basics are easily visualizable and understood.
Yes.
Probably help with virtual reality, though, you know?
Exactly, yeah, correct. So dump us right in. This is so interesting. So they'd go up initially, and they'd land within the commercial resupply. Then the astronauts that are in the ISS would take the small sats and push them out of the airlock.
Kind of. There's a few more steps to it than that, but yeah, absolutely.
That used to be the path, and then they would unfold and start imaging and then talk to the ground stations. But now you guys go up, and then you're deployed at a different stage rather than all the way up to the ISS.
We actually go higher than the ISS.
You go higher now.
The ISS is very low.
250 miles.
Right.
And you now go 300 or so miles.
Well, no, actually, I don't think in miles. I think in kilometers.
Okay.
And the our normal orbit is about 500 kilometers, and the ISS is significantly lower than 500 kilometers.
It's like 400, right?
440, 420. I think it moves around depending on these debris events, but more so depending on. They don't want it to get too low because then there's too much drag, and then it gets even lower, but they don't want to necessarily have it be too high because they're spending a lot of time looking at the Earth, and it's actually nice to look at the Earth when you're a little closer.
Yep.
I mean, that's one advantage to our ISS deployments is that they're closer, so they see things at higher resolution.
Yeah, that's an interesting point. So, okay, so now you're flying further past it and being deployed further past it.
Right, and we're being deployed by rockets without any people, and so there's no one to watch it. Sometimes there's like selfie cams on the rockets that see the things deploying. In fact, that's in the video. There's a big our big 88 sat deploy, I think, is captured partially on that video.
Yes. So now you're usually going up with other satellites and other resources.
We've had a few dedicated launches, smaller rockets.
That's huge.
Yeah.
Ron, let's go to the next slide.
It's just a video, I think.
Wait, what? No, wait. What about the small sat? What about Dove, the white satellite?
This one here?
Yeah. Perfect. Well, I want to I want to at least give a detailed. All right, everybody, tune in very close detail right now. Okay, so I'm gonna start, and you're gonna interrupt me if I'm doing things incorrectly.
Sure.
So these are the foldable. So these fold back in because it's deployed as just one rectangle.
Right.
And then this is covered. This lens cap is covered as it's deploying. So then as it pushes out, as it gets put into orbit, then this the lens cap comes off, the wings jut out so the solar cells have room to breathe. There's more solar cells here on top. Then
the solar cells are on the other side of the white panels.
Correct.
Those white panels are just decorative.
And they're beautifully
they
decorative.
They have animals and radio waves and all kinds of stuff
Exactly.
on them.
They're so cool.
That was Forrest Stearns, our art director, who got us all into putting drawings on the satellites. First his drawings, but then eventually everybody's drawings and their kids' drawings and contests for drawings. And
that's
so
awesome.
Every satellite that goes up is covered with art.
That's great, and because you can't actually put solar cells on both sides of the panels.
Well, the sun doesn't shine on both sides of the panels in general.
But you could. Then you wouldn't have to move the.
Well, you're right, I suppose, but you also really need to radiate heat, and white is good for radiating heat. In fact, one of the constraints on the drawings is that they don't have too much ink.
Too much black ink. Yeah, that's interesting. Okay, so now, so this is the telescope side. On the telescope side, you have a 3.5-inch mirror. And that's continuously taking the light that's reflected from the Earth and capturing that light. And then you have a camera here in the system on the back. The camera system captures that, and then it holds the data until you go over the ground station, and then the radio transmitter sends the information to the ground station. There's so many other important pieces on this that I'm skipping.
You've got the basics. You've got the basics right, and sure, yeah. And there's a bunch of other components and a bunch of operational modes, but that's the basic idea. Take pictures when you're over land, mostly, and sometimes when you're over water. Charge your batteries when you're over water in the sun. At night, when you can't charge your batteries or take pictures, send data down to the ground stations when you pass over them. By night, day, that happens every 45 minutes. You go from night to day or day to night, because it takes about 90 minutes to do in an orbit.
Yeah. That's so cool. So if you're flying over water, you're recharging as if the sun's up.
Yeah.
And then if it's nighttime, you're trying to fly over ground stations so you can give
downlink. Is the
downlink. That's so interesting. I love all of this nuance, and I love seeing this, and I'm so happy. And Ron, if you can do a quick capture with one of the RoboCams up at the satellite imagery that we have.
Oh yeah, I don't think that's ours though. I'm not sure if I want to advertise that imagery.
Basically, what we're trying to get at least say is that this is, you guys have taken a lot of really important photos of Earth. A lot of companies have taken important photos of Earth, and you have everything from Bora Bora to the Chilean coastline or Argentinian coastline, one of the two, to South Korean refineries and Chinese dams, the Golden Gate Bridge, Palo Alto, Redwood City, and those shipping yards for where we transit all our goods. Just all of these different amazing things. You can teach us a quick one. This is really important. You're observing climate. You're observing crop yields. You're observing urban area planning, disaster response.
Yeah, all those things. Climate, not so much. I mean, we look at ecological things like deforestation and agriculture and coral reefs. But climate, we don't really do climate. Climate is a specialized type of satellite that needs very super precision temperature readings and radiation radiometers and bolometers and things like this. So that's more of a NASA thing.
But deforestation and coral reefs are definitely still in the ballpark-ish.
Oh yeah, we definitely, I mean, look, we just imaged the Earth, we imaged the coasts, we imaged the land, we imaged some things out in the ocean. The uses of that data are just manifold and more all the time. Now, a big emphasis at our company is on analytics, which means nobody can actually look at terabytes of images. That doesn't make any sense. What they want is actionable information. How many houses were built in this province in the last month?
Wow.
How many trees were planted, you know, in this region?
Yeah.
Are there any new roads in this region? Are there any ships moving around that don't correspond with ships on the ship tracking radio system?
Yeah.
It's a big issue because ships try and spoof where they are so they can go fish where they're not supposed to and things like that.
That is nuts.
So yeah, so we're got customers who have all these different modes of utilizing the data, and it keeps bootstrapping up to higher and higher levels, where now we're making automatic time series so people don't have to look at images at all, or we find when something has changed and then we task one of our high resolution satellites to go look and see what's actually changed, and then if it's a change that triggers a certain alert, maybe a human will go look at it. Yeah, it's all kind of moving up to ever higher levels.
It's so cool that you can start using image processing, machine learning for image processing, so you can see if things have changed drastically to the point where you need a human to come and look at it and be like, whoa, look at that crazy change, or how many people are moving into a new area, how many new houses are being built, or...
Well, people, we can't really see people.
The fishing one was crazy.
We can't see people, our satellites, even our high resolution satellites.
Well, you see houses. You see houses being built.
But as we know,
so
in
that's
China
crazy.
and stuff like that, there's tons of houses, or even in the US, they put houses with no people because, you know, they miscalculate their real estate development projects. Anyway, but
how many people
nonetheless.
The fishing one was crazy as well. That one was nuts. But these are all such interesting use cases for small sats, for imaging the Earth.
And if anybody has a use case or a project that they want to do, they should go to Planet's website. We have a free data program.
Links in the bio, planet.com.
Right. We have you can sign up for certain amounts of free data. We have Open California, where you can get, I think you can get all of California, including historical. And if you're an academic or a nonprofit or a non-government organization or even a citizen scientist, you can utilize our data without having to pay anything, or without having to pay much, depending on how much you want.
Bless Planet for open sourcing so much of their data.
Well, we have to pay the bills, and
you do have to pay the bills.
And so, if you want huge amounts of data that's up to the minute, you're going to pay for it. But if you want small amounts of data for a science project, you will try and accommodate.
That is so awesome. Seriously, bless you guys for doing that, and we hope to be able to support you in every single way, because imaging the Earth is so important for everything that you just listed. I think I saw on the Wikipedia page there was you were capturing a volcano slowly emitting smoke. So it was starting
we captured all those lava flows in Hawaii as they marched on. Yeah. It's, I mean...
That's crazy, and you could warn people and be like, get the hell out of that area, lava's coming your way.
Yeah, disaster preparedness, disaster response is important. One of the important things with disaster response is when a disaster happens, all kinds of satellites start looking at it, but they weren't looking at it the day before or the week before. Our satellites were.
Yes.
And so we can tell you what got covered up and what was there, and we've had a lot of
That's great
success in that.
Yeah,
we have this sort of time machine where we can go back in time to any place, anywhere on the Earth, go back in time and see what was. And it doesn't matter how many satellites you have, it doesn't matter how big your satellites are, if you aren't imaging the whole Earth every day, you can't go back in time. You're
like the Wayback Machine, but for satellite imagery.
Point. Yeah, right.
Yeah, I love that. That's so important to be able to have. Okay, this has been such a pleasure. I'm so happy to have learned more about aerospace engineering, orbital mechanics, satellites, small sats, all the nuance of the engineering of those and how they work in working with the Earth. It's amazing. Just a very couple quickies that we like to ask our guests on the way out.
Sure.
Do you think we're alone in the cosmos?
I think we should behave it. I think we should cherish our consciousness and our planet and our future as if we were alone in the cosmos. I kind of hope we are alone in the cosmos, because if we aren't alone in the cosmos, the scenarios don't look so great. I'm aware of the great filter controversies and the doomsday scenarios, but yeah, I obviously, no one knows if we're alone or not, or no one should say they know, but I believe that until there's clear evidence to the contrary, we should comport ourselves as if we're alone, because we may be the universe's one experiment with intelligent life. So let's make sure we get it right.
Yeah, God bless the consciousness having evolved on this planet. Yeah, thank you for making that a very clear point. Do you think that we're in a simulation?
Oh, we're in the simulation TV show, so I guess we are. No, I do not, but that's a long discussion, right? There's a lot of technical reasons why I think we're not.
That you think we're not?
Well, I think, yeah, I think it's highly unlikely. And again, I think we should comport ourselves as if we are not. I think nothing would be stupider than to act as if we're in a simulation, because what if we're wrong? It's like, I mean, this is a general sort of nihilist attitude, right? It's like, oh, it doesn't matter if we blow ourselves up. There's thousands of planets with life throughout the galaxy, and intelligence is common. So who cares what happens to humans?
Yeah, but that's
very anti-human,
that's one
nihilistic
side of that's a very straw-manned argument on like what is the steel man version of the argument of.
Well, the reason I brought that up was not to knock the SETI or something like that, but to say that the simulation argument seems an even worse form of that. It's like, not only does it's like, there's nothing we can do. Like we can shut off at any time.
Oh, we did?
Yeah.
Interesting. I wonder if that's due to the battery or what. It's okay. Is that on one of the two? Yeah. It's okay. We'll yeah.
See?
Yeah. We'll close the show. They shut you down. Oh my God. Okay. Here we'll use. Ron, can you hear me on this mic? Right?
Yeah.
Okay. Cool. What do you think is the most beautiful thing in the world?
What do I think? You're going to have to give these questions out in advance. The most beautiful thing in the world to me personally, or just overall? I think I think one of the most beautiful things in the world are some of the things that you see with psychedelics. But obviously the creations of humans, like the great cathedrals and the great works of art, are beautiful, and of course nature is also beautiful. So I have no idea to answer that question. I tend to not be an absolutist that has one favorite anything. Like I couldn't even tell you what my favorite food is, much less what's the most beautiful thing in the world. Yeah. So, you know, but let's keep trying to find out.
Psychedelics do unveil some interesting aspects of reality. Thank you very much, Creon. Thank you so much for coming on to our show. We greatly appreciate it.
Thank you for having me. It was a pleasure. And now you've got a new Patreon supporter and a new audience member in me.
We greatly appreciate that so much. And you heard it. You heard it here first. All this amazing stuff about aerospace engineering. Definitely go and tune in more into aerospace engineering and space and the cosmic perspective, the overview effect. Why does all of this matter? Go and create with this content. Don't just consume. Go write about it. Go make videos about it. And go and inspire other people to care about it. Start businesses about it. Subscribe, comment below. Join the family. Join the conversation. Join us on Patreon. You heard it here from Creon as well. Join us. Support us. Help us grow this. Help us impact more people with this. Much love, everyone. Thank you so much for tuning in. Thanks, Ron, for producing and directing.
Thanks, Ron. Thanks, Tom.
All right. Much love. See you guys.